A bit of British stuff kicked in accidentally. Okay, let's have a look then at where we are right now. We're going to look at the equation of a plane. And to find the equation of a plane, basically, we use this formula. So you need to know a point, x1, y1, z1, and you need to know a normal vector. So we'll start off with a very simple question, a version of 21. They tell me the point, and it's not as straightforward as I thought. Okay, question 20 there. So they tell us a point, and they tell us that the direction vector is -1, 4, and 5. So that's my ABC, and that's my x1, y1, z1. So -x plus 4y plus 5z, and then you do a dot product. So you go -1 times 8, 4 times 1, and 5 times 2. And in this case then, it's -x plus 4y plus 5z, -8, -4, 6. And that's the equation. Now that would be the simplest possible way that you could be given information to create, to find the equation of a plane. Just tell me the point and tell me the normal vector, right? And I apologize, normal vector, there we go. But they might tell you this. They might tell you a point and that the plane that you want is parallel to this plane. Now, if you are parallel, right, if you have two planes that are parallel, these numbers here are the normal vector. Agreed? And so haven't you just disguised the value for the normal vector? So if two planes are parallel, shouldn't their normal vectors at least be equal or multiples of each other? It really doesn't matter. If you make them multiples, it just means they're further apart or they're longer or something, right? Great. So they either tell you the guy or they tell you something that allows you to find the normal vector. Let's look at 21 then. They're giving me a point and it's parallel to this guy. Nothing's going to come easy. That's my x1, y1, z1. It's parallel to this plane. But the way this plane is written is not the way it needs to be written if I'm going to find the normal vector. So what I'm going to do is I'm going to say 4x, take away 4y, minus z equals 0. So I'll write that again because I made a mess. Are you comfortable with this being the same as that? Can you see algebraically how to do that? Could I have done the following? Minus 4x plus 4y minus z equals 0. Wouldn't that also be correct? Do you see that we already have got that problem of non-uniqueness? What do you mean by that? If I use this form, won't the normal vector be 4, -4, -1? If I use this version, won't the normal vector now be -4, 4, one of these two guys, there we go, +1. If I use this one, won't the equation look different than if I use this one? So you have to be aware that there are many different versions of the right answer to the equation of a plane. And we just keep our fingers crossed and hope that WebAssign has them all stored. So you don't put the right answer in and it just says you're wrong because it's not one of the 5 it's got, right? You found a 6th one that they haven't thinking of. Now you put this together. What do you want? I'll pick this one. So the equation is going to be 4x, take away 4y, take away 1z, and it's going to be equal to 4 times 1 plus negative 4 times 2 plus negative 1 times negative 3. And so 4x, take away 4y, and that's 4, and that's negative 8, so it's negative 4, and then final number, I believe is that. So just tell me a point on the plane and tell me the normal vector, or at least some way to get the normal vector. Tell me the equation of a plane that it's parallel to. If I doubled, well, let's do it by 5. If I multiplied everybody here by 5, wouldn't that also be the equation of the same plane? Agreed? Do you see the problem with non-uniqueness? That everybody could do it in a slightly different way and come up with a slightly different, or maybe even a majorly different looking answer. There is a way to standardize it, but nobody does it. Couldn't I do it in such a way that I make the normal vector a unit vector? Wouldn't that at least make everybody get the same answer at the end? But we don't typically do that, so I'm not going to either. Now, question 22. Let's find what it is. We want to find the equation of a plane, and it contains this line. So it contains the line x equals 3 plus t, y equals 3 take away t, and z equals 5 minus 3t, and it's parallel to 5x plus 2y plus z equals 7. Now, what I'm going to do for the next question, maybe the one after that, I'll see how things go, is I'm not going to get the entire answer. All I'm going to do is find a point and find the normal vector. Because see if we get those two, can't you finish the question off yourself? Right. Now, since it's parallel to this plane, won't its normal vector have the same values, 5, 2, and 1? Are you comfortable about if you're parallel to me, your coefficient of x, y, and z will be the normal vector I need? Now, this plane contains that line. So can you imagine this is the plane we're getting, and that's the line and it's embedded in it. Don't I now need to get a point on the plane? How can I use this information that this line is contained in the plane to find a point P?
Did you plug that into the parallel to equation?
Well, you could, but if you did that, you might be annoyed to find out that you get 0 equals 0 or 7 equals 7.
Well, at least we'd know it was parallel then.
Well, you'd know it was embedded, which it is.
Can you just plug in any t value?
Yeah, and if Molly plugs in 2 and Tim plugs in 22, won't we end up with lots of different answers because of that? Right, so I'm going to plug in 0 because I make mistakes, and doesn't 0 just make it less likely I'll make a mistake? And so if you plug in 0, don't you get the point 335? Now, if you put them together, would you get the equation of the plane and call it good, right? So dot, 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 right? You finish that one. How about this one? I have got the point P 0, 2, 2, Q 2, 0, 2, and R 2, 2, 0. Can you imagine P, Q, and R looking like this? Now, P, Q, and R make a triangle. You agree? But won't P, Q, and R make a plane? So we want to find the equation of a plane that passes through 3 points, P, Q, and R. And to do that, all I need to do is find a point on the plane, and I need to find the normal vector. Would you agree? Once I get those two, we're good to go. Okay, let's make life easy for you. Tell me a point on the plane.
0, 2, 2.
And I might as well pick that one because that's what I call P. But theoretically, couldn't you pick 2, 0, 2 or 2, 2, 0 if you felt like it? Right? So there's 3 choices. Fine, that's good. Now, the normal vector is going to be a bit trickier. The normal vector would look probably something like this guy here. Right? Isn't the normal vector perpendicular to the plane, right? That's how we define it. How am I going to find that guy?
Using cross product,
Okay, cross product of who?
PQ and PR.
Are we comfortable about why that works? Does that seem reasonable? PQ, PR, cross product. So let's find out who PQ is. 2 take away nothing is 2, nothing take away 2 is -2, and 2 take away 2 is nothing. That's PQ done. PR. 2 take away nothing is 2, 2 take away 2 is nothing, nothing take away 2 is -2. Okay. Then our normal vector is the cross product of those two. So we have an I, a J, and a K. And we have 2, -2, 0, and 2, 0, -2. So many I's. Take away so many J's, plus so many K's. Okay, cover that guy up. 4 take away nothing gets you 4. Middle guy, -4 take away nothing gets you -4. End guy, nothing take away -4 gets you 4. And we end up with 4, 4, 4. Now that we know those two guys, can't we get the equation of the plane? Right, we know the point 0, 2, 2, and we know 4, 4, 4. Right. I suspect these numbers are all the same because of the pattern that's here, right? You know, if I change that to a 1, I bet you this would change as well. Any questions about that strategy? How do you find the equation of a plane passing through 3 points? Okay. 24 is just like that. Last question. Cool. We can start the next section after this. Find the equation of a plane. Okay. This is a killer. Let me show you the question first, and then I'll that way I can kind of break it into its pieces later. We want to find the equation of a plane that passes through the line of intersection of this plane and that plane and is perpendicular to this third plane. Whoa. So we have to find the equation of the line that passes, that's the intersection of these two. And the reason why we need to find the equation of that line is that won't that line be at right angles to our normal? And since this guy is perpendicular to it, won't this guy also be at right angles to its normal? So our normal vector will be the cross product of those two things. So that's a lot of work just to find the cross product. Secondly, don't we also need to find a point on the line? And that's going to take a fair amount of thinking as well. So I'm going to just start with the line that gets formed by the intersection of the two planes. So let's just focus on that for a minute. I want to find the equation of a line, or at least its direction, but equation will be nicer, of the line that is that. So can you imagine that's one of them, and this is the other one. Can you see that two planes do intersect? If they can, let's phrase it that way, can't two planes intersect on a line? So we want to find the equation of that line. Because if I can find the equation of that line, can I also find a point on that line? And won't a point on that line be P, the point in the plane that we need? So we're going to get a lot out of this. I'm going to call this equation 1, and going to call this guy equation 2. And we have a big problem here, don't we? Don't I need to know, to get the equation of a line, don't I need to know the direction vector for that line? And don't I also need to know a point on that line? Great. Molly, have you got an idea?
No, I was just thinking that it's nasty.
It is nasty. So let's think of it outside the box. If you look at this red line, isn't it perpendicular to the normal of each of those two planes? Right. This red line is in the first plane. If you're a line in the plane, aren't you perpendicular to that normal? But isn't this red line also on the other plane? So isn't that red line also perpendicular to the second one? So if you look at the normal of this one, I'll call it N1, isn't it 1, 0, -1? And if you look at the normal for this one, the second one, isn't it 0, 1, 3? So what will the direction vector of the line be? How will I find the direction vector when I know that it's perpendicular to these two? Yes.
Cross product.
Cross product. It's not as ugly as you thought it was going to be, is it? So cross product of the two normals. So if you want to know the direction vector for the intersection of two planes, it's the cross product of their normals, essentially. So this is going to be I, J, K. 1, 0, -1, 0, 1, 3. So many i's, take away so many j's, plus so many k's. 0 take away -1 gets you 1. 3 take away nothing gets you 3. 1 take away nothing gets you 1. So the direction vector is 1, -3, 1. So you agree that's the direction vector of the line. Now, that's good. Let's find a point on the line. If you are a point on the line, x take away z equals 3, and y plus 3z equals 2, right? If you are a point that is on both those planes at the same time, don't you just need to find an x, y, and z that is true for both equations? Now, there is a little bit of a problem, but it's actually an easy fix. Aren't there 3 variables, but we only have 2 equations? So don't try and solve it as a system of equations because you don't have enough information. But I'm going to do this. I am going to make z equals 0. Now, if I make z equals 0, won't x be equal to 3 and y be equal to 2? Haven't I now found a point on that line? Great. Could I have made z equals 1? Yeah, and I would have got a different point. Could I have made it 42? Could I have made x equals 0? Could I have made y minus 42? Could I make anything I like a number, right? Pick x, y, or z and pick a number. Of course, every time you do it, don't you end up with a different point on that line? Well, we got everything that we need. Now, to go back to the story, I'm not actually going to get the equation of the line because I don't really need to go that far. But what I do now know is that my plane is perpendicular to that line, and my plane is perpendicular to the plane x plus y take away 2z equals 5. So it's perpendicular to 1, 1, negative 2. So I have a point P that's on the plane. Right? We've established that. I'm now going to find the normal vector for this plane. And what do I know about it? I know that it's right angles to this guy, and I know it's at right angles to this guy. So I got to call that M1 then, won't I? Right. So my normal vector is going to be the cross product of those two guys. So can you imagine this red line represents the intersection of the two planes, and then we've got a plane that passes through this guy, right, and is at right angles to this plane. And so we know that the normal of those two is going to be the cross product of these. So it's going to be so many i's, take away so many j's, plus so many k's. So 6 take away 1 gets you 5. Negative 2 take away 1 gets you negative 3. And 1 take away that guy gets you 4. So I am looking at 5, 3, 4.
Hold up, where'd you get 1, 1, negative 2?
This guy here, I got that from here. In the question, they told us that it was perpendicular to this plane. So it's 1, 1, negative 2. They told it was that one. So the normal vector for this one is 1, 1, negative 2, and that's where that came from. So this was given to you later on in the question. Are we good? Right, you put that package together then. I have a point 320, and the normal to the plane is 5, 3, and 4. So the equation will be 5x plus 3y plus 4z equals 5 times 3, 3 times 2, 4 times nothing. And we are finished. The equation of that plane is that. It's probably the worst case scenario where the information they gave you was well hidden. They didn't tell you a point P right off the bat. They didn't even tell you some information that you could get the normal vector really quickly. We had to do a whole load of other things just to come up with that. But we are finished. Any questions before we move on to our next section? You're probably going to have to look over that again slowly when it's your own time. So let's change tack and look at our next section. Give me a few minutes to load the damn thing up. At least get its heading. We are going to look at what are called vector functions. And it's a new chapter. Okay, where are we? Here we go. When we talk about vector functions, you'll very often hear the term space curve. We're going to describe a function using that notation. You know, me personally, I would probably have used that notation, but it is what it is. And you can get a guy and that is an example. And so is this. Of a vector function. What does it look like? Well, if you try and sketch it, it ends up looking like this. It ends up with a curve in 3D space. And when you plug in t equals 0, you might get that point there. And when you plug in 1, you get that point, and plug in 2, you get that point, plug in 3, plug in 4. So can you imagine you could take little snapshots of it? But this is in 3D, right? So you won't imagine this curve as like a bent piece of wire in 3 dimensions. A good analogy, can you imagine a jet flying in zigzag kind of movement in 3D space? What you're really plotting when you think of a vector function is the pathway of an object. And do you notice that it has an orientation? And that just means what direction are you going? Are you curving up the way? Are you curving down the way, right? So that's a little bit different from 141 where functions are just flat 2D shapes, right? In 3D space, vector functions, and they're called vector functions because we describe them in terms of a vector. These vectors are called position vectors. They're essentially telling you the coordinates of the point in 3D space. And it's called a position vector because you do it as a vector from the origin. So if the thing was 1, 2, 3, it would be a vector from 0 and going 1, 2, and 3. Wouldn't that be the same thing as the coordinates? But it's convenient for us to think of it in vector notation. It just makes life so much simpler, right? So far, so good. Right. So let's look at, if I've still got it online, and I think I did, but who knows where I've put it. Are you coming through? It is. Okay. Let's show you, if I can, the software that allows us to sketch these guys. Oh, by the way, this is just 2 planes intersecting on a line. I didn't show you that, but that's what that was. Right, so let's go away. There you go, go away, go away. Right. Should be able to delete these guys. Normally just click, there we go, delete and delete. Okay, now I'm going to do a little bracket. I'm going to go t, comma, cosine t, comma, 3 sine t. And probably zoom in here. There. There. Can you see this guy in 3D? Doesn't it look a bit like a spring? A slinky. That's an example of a space curve. The grey plane that you see is just the XY plane. That's helpful to show you where the floor is. Now, if I change this guy and I don't know, it's already doing the thing. I need to make this bigger. My eyesight's just not good enough. There we go. There, I can see it much better as well. Okay, let's go back into this fella here. I think it's going to be, delete this one. And let's do a 2t take away 1, a 3t take away 3, and a 1 take away t. Do you recognize that as a straight line? Yeah, you see it? Equation of a straight line. So aren't straight lines just a vector function? And you can put any function you like for the x, y, and z components, and it will sketch it for you. So since we're introducing a new function, I think we should focus a little bit on some of the fundamentals of it. Vector functions in 3D are described like this. When you are asked to find the domain of a vector function, what you're looking for is the usable values of t. Isn't the domain the usable values of x, right, in 141? So suppose I have a space curve and it's 1 over t square root of t plus 1 and t squared. And I asked you to tell me what the domain of this space curve is. What you're looking for are what values of t can I actually get numbers, right? Because would you agree in some places things are not defined, right? And you can't use them. Now, this one's a bit messy, and I chose it to be messy. Would you agree that this guy is okay, but you can't use 0? What's the usable values here? What does t have to be greater than or equal to be usable in a square root like this?
-1.
Okay.
Or, yeah, greater than -1. Because
Right.
if you're less than -1, you're going to meet square root of a negative number.
Right.
Unless we want to, if we want to limit it to real numbers in that.
Yeah, everything we're doing is limited to real numbers. Would you agree t squared doesn't have a problem, right? You can use it for anything. So what you need to do now is you need to combine these two restrictions. And the typical way to do that is to use a guy called interval notation, which is a way back in 141. Remember interval notation, curved brackets, square brackets, and so on. So if I wanted to describe all the points greater than or equal to -1, but don't use 0, when I do a square bracket -1, that means you can use -1. I would then go all the way to t equals 0 and do a curved bracket, union, curved bracket, 0 to infinity, curved bracket. Curved brackets mean you cannot use that value. You can't use infinity because infinity is not there, right? It keeps going. Are we happy with that one? Suppose I gave you another space curve. And I'm saying find its domain. But this time it's going to be that. So what you do here is you find out what the issues are, and then you combine them into a single, interval notation limit. So this would be the domain of that function. Right, in this case, what are the usable values in a function 1 over the square root of t minus 2? You can't use every value of t, right? There are restrictions. What are the restrictions? What does t have to be usable?
Greater than or equal to 2.
Are you allowed to equal 2 in this case? Not this time. Yeah, you can get 0, but isn't 1 over 0 bad news? So you can't use it for that reason, right? So greater than 2. What about e to the power of 1 over t squared? Any problems with that? Any value of t that could cause issues? You agree 0 causes problems? So I'll write that down as don't use 0. What about the natural log of t? For what values of t can you find the natural log of something? What values of t can you find the natural log of something?
Don't they have to be positive?
It does. Now, you have to be a little bit careful. We have to combine all of these restrictions into interval or intervals, right? So what do I know? It has to be greater than 0, and it has to be greater than 2. Well, if it has to be greater than 2, doesn't that supersede this one? So I can ignore that one. It has to be greater than 2, and it's not allowed to equal 0. Well, if it's greater than 2, it won't be 0. So doesn't it get superseded again? So you see in this example, although there were 3 restrictions, didn't this one pretty much supersede all the others? And so the interval of the domain is the interval 2 to infinity. Don't use 2. Does that make sense that sometimes the restriction doesn't matter because something else later on, you know, takes care of it? So domains, don't get a lot of questions, but that's how you find domains. Let's look at how do you find the limit as t tends to say infinity of a space curve. So let's look at how you find the limits. We're looking at 2 kinds. The limits as t tends to infinity and the limits as t tends to some number, because sometimes that causes problems. So first one would look like this. Okay. How do you think you find the limit as t tends to infinity of a space curve?
Take each individual part and find its limit as t approaches infinity.
That's it. Isn't it? Does intuitively, doesn't that make sense? Right? You just find each one separately. So we're going to find the limit as t tends to infinity of this guy. And the middle guy. And the last guy. When you do limits at infinity, isn't your main go-to methods brute force? You know, just plug infinity, L'Hopital, or divide top and bottom by t or t cubed, right? That kind of technique. I'm just going to cut to the chase here, but I'll tell you the method. Well, maybe I won't tell you the method. You tell me the method. What's the answer to this limit as t becomes infinite?
2/3.
Okay. I know you could do that in your head, but if you wanted to prove it to me, what method could you use to get 2/3?
Divide by
L'Hopital.
t.
Divide by t or L'Hopital, right? Both would work. Correct. I know that looks weird. What's e to the power of 1 over t going to get you? It's going to get you 1, isn't it? Couldn't you do that just by brute force? e to the 1 over infinity, e to the 0, e to the 0 is 1. Okay. What about the last one, 4t squared over 5t cubed plus 1? What would be the limit of that guy as t goes to infinity? You could do L'Hopital twice. Yeah, you get 0. Someone did that. Do L'Hopital twice or divide top and bottom by t squared, whatever way it works, you get 0. So now we have to try and imagine, what does this tell us about this space curve? Well, we know what space curves typically do. They curve, right? And it curves like this, perhaps. But, you know, that's t equals 0, t equals 1, 2, 3, 4. But can you imagine that eventually, doesn't it just shoot off in a straight line direction? And in this case, it shoots off in that direction. So can you imagine at the end of its life, it's virtually a straight line. And not only is it a straight line, won't that straight line be a vector in that direction? So doesn't it kind of tell you the direction that a vector is traveling in once you have large values of t? Are we cool with that? I see a smile. Smile's good. I like smile. Smiles mean, yep, I know how to find limits, so doing it 3 times isn't a big deal. And now I've got a kind of idea of what it's telling me, right? So for our last kind, how do you find the limits as t tends to a number? Well, let's suppose I give you an example of that. Oops. No, I'll keep that one. That's acceptable. Okay. If it's t tends to a number, it wouldn't surprise you. Don't you do each one separately, just like you did the other time, right? So let's see what we get here. We're going to do the limit as t tends to 2 of t squared plus 1. Oh, well, isn't that just plug in? And if you plug it in, you get 4 plus 1, you get 5. So that's 5. This guy, how would you find the limit as t tends to 2 of that guy? And I want you to think back to Calc 1. What method could you use to find the limit as t tends to 2 of that ugly fraction?
You do L'Hopital?
Yeah, L'Hopital's a good to, good to go guy. I believe it's 2 over 2 plus 2. It's 2 over 4. You can check it later, but I believe the answer's a half. For something like e to the power of 1 over t minus 2, wouldn't you do 1 e to the 1 over and just brute force it? Would you agree that e to the 1 over 0 is e to the infinity? And in which case, won't this answer be infinite? I mean, some limits can be infinite, right? I mean, that's just what they are. Are you comfortable with brute force e to the power of 1 over 0, e to the infinity, and e to the infinity is infinite? Well, what would that one look like? Well, that would be a little bit trickier to imagine, but it can be done. This guy here is essentially telling me that we have a problem at t equals 2. And at t equals 2, the z component is infinite. So can you imagine that this curve does the equivalent of a vertical asymptote at t equals 2? So you imagine it's doing its nice little thing, but as you get close to 2, it goes vertical upwards. Now, why vertical upwards? Because infinity is z, and isn't z vertically upwards, at least in the orientation I've drawn it. If the infinity was here, wouldn't the thing zoom horizontally in the x direction? And if infinity was here, wouldn't it go horizontally but in the y direction, right? So what you're looking at here is the equivalent to what we would call a horizontal vertical asymptote, right? The function is basically, you know, zooming off somewhere really bad, right? It's got a big issue. You do not want that, but I could imagine, what could I imagine doing that? Can you imagine an object traveling far too near to a black hole than is safe? Couldn't some really weird thing happen to it when it gets caught, right? It gets sucked into that black hole and who knows what the heck happened to it. Maybe that would be a model that would represent this. That's the only analogy I can think of at this moment. So your last name and